Hello, guys.
Hey.
Well. So, I think we should start now. Okay. So starting from today, we are going to discuss about, well, it's a little bit noisy, I think. Starting from today, we are going to discuss about the Fourier transform on the whole space. Okay, now it's not, we are not discussing about this periodic function, but instead we are going to discuss the general functions with some other boundary conditions. Okay, and then the problem could be somehow different from what we deal with, which is those kind of periodic boundary conditions or these periodic functions, and then you use periodic function to solve your problem. Okay, but now what we try to do eventually are somehow we try to, in general, solve some other kind of problems with, well, the domain to be somehow like, well, we discuss about this kind of square. And then, now what about we are interested in a circle or a disk? What if our domain is on a disk? We want to solve the Laplace equation and or this heat equation and satisfy some boundary condition. And what we can say about the solution. That would be something we are going to discuss, okay? Because you know, for instance, in the material science, well, your material may not be this kind of square, it may be some kind of disk, right? And in that case, how can you study the the heat conduction on this material? Then maybe you will need the heat equation on the disk instead of a square, okay? So again, this part will need some kind of analysis, background knowledge, and instead of the convergence stuff, we will use some kind of integral instead of convergence. Okay, and in this part, well, this integral, I think those kind of improper integral is something I hope you are more familiar with. More than the series or this kind of sequence stuff, okay? So let me first try to tell you what kind of function we are going to discuss, okay? Because when we try to discuss so-called the Fourier transform, what we're trying to do is we're trying to take the total integral of some functions pair with e to the minus 2 pi I xc dx. Okay, this eventually we call it the Fourier transform of our function. You can see that it's somehow similar to what we've learned before, right? Which is f hat n. Well, because we just change this n to be some c and take the integral instead of the period of this function to this whole domain, this whole R, okay? So it's somehow, so we should think that this may share some properties of our Fourier transform. One of the most important property we are going to use to solve the partial differential equation is when you have the derivative of a function, okay? When you have the derivative of your function and then you take the Fourier transform, it should be somehow like something like c times the Fourier transform of your function, okay? Just similar to this kind of Fourier coefficient. And in this case, we know that then if you have a partial differential equation, and then if we take the Fourier transform of some variables, then what you have is you will transfer your partial differential equation to maybe an ODE, maybe even an algebraic equation, okay? So, which makes the problem solvable. Which is why we are interested in this kind of, well, transform of a function. But of course, if we would like to do this kind of transform of a function, what we will need is we will need this kind of integral, like the whole space integral, to be something valid for a function. So in this sense, we first need to have this, I need to write down what is this kind of, well, improper integrals definition is, and then I have to tell you for what kind of function you are able to do this kind of Fourier transform, okay? So, which is, we want to see what kind of thing you are able to do this Fourier transform so that you can use this kind of for instance, very good functions to deal with some PDE problems, okay? So that's the, we define, well, this is Fourier transform, which is on chapter 5 of Stan's book, okay? And we define this kind of whole area integral to be, for a function, to be the limit as n goes to infinity from minus n to n, fx dx, okay? So it's somehow similar to, well, to what we have this called the partial sum, like the Fourier coefficient, right? We try to define, well, the meaning of this from infinity to, minus infinity to infinity of the total integral of a function. This is just like you take the partial integral of this function and take the limit as n goes to infinity, okay? If you still remember, if you don't, then that's all fine, you just forget about it. But if you still remember the improper integral we define in calculus 1, then you may find that this kind of thing is slightly different from what we define, which is you take this limit from minus n to n, not from something not symmetric, okay? Not from minus m to n. But I would say, well, at least in this course, it doesn't matter, okay? Because what we are interested are those kind of functions which are really nice when we try to do the Fourier transform. So what we will discuss, it will be the same no matter whether you take from minus n to n or from minus n to 2n and take n goes to infinity, or from minus n squared to n as n goes to infinity. Okay, it doesn't matter. So if you don't remember this, then it's fine. So you just see, okay, this kind of definition is just from minus n to n. Okay, no more than that. Then, in this kind of definition, if we would like to, well, somehow do some surgery or manipulate our function in this way, then probably we want this kind of integral to be something makes sense. Okay, so what we're trying to say is, now let's suppose our function will decrease very fast so that we are able to take this kind of a limit. And in that case, we are able to, we'll even multiply some functions like e to some power and then take the integral. Okay, so that's trying to assume everything is perfect and we are in a universe of, well, very, very good function. Okay, and well, we call this kind of function to be moderate decreasing. Okay, a function f defined in R, well, on R, is said to be of moderate decrease or moderate decay function, moderate decrease, if f is continuous and there exists some a greater than 0 such that, well, your fx decay can be controlled by x squared, okay, for any x in R. Which means when x is very big, then your fx will decay, well, or will not increase, at least bounded by 1 plus x squared. Okay, This doesn't mean that your function should be monotonic. It just says that eventually it will not be so big. Eventually, for instance, this 1 plus x squared, this function looks somehow like this. Looks somehow like this. It's smooth. And your function, your f, could be anything. It may not be monotonic, okay? But what we want is your function to be not to be very big eventually. It is somehow can be bounded above by this 1 over 1 plus x squared. It could be somehow oscillate a lot. But if you see it in some kind of large scale, then, well, you can see that more or less it will decrease, like 1 over x squared. And why I say, well, this kind of decay is just for those x that are very big. Well, it's just because when x is not so big, we assume that your function is continuous, right? So which means f itself is somehow bounded above. So when we say f is continuous, and then we try to say some good property of this function, then probably what we want to say is, okay, you have some control about the decay of this function, okay? In that case, you can see that, okay, it has no singularity, so-called singularity, which means your function will not somehow blows up like 1 over x, like this kind of case, because your function is continuous. And moreover, this function will somehow decay at infinity. So which means if you try to see the whole real axis as some closed interval, then this function has no this kind of singularity like 1 over x on this whole interval, not on any point of the real axis, not even at infinity. Okay, at infinity is also very good, and it even has some decay at infinity. Okay, so f continues, no this kind of point. And f can be bounded above by 1 over 1 plus x squared, so f should somehow looks like this. Okay, so well, when x is very big, this a over 1 plus x squared is basically like a over x squared. Right, so which is why I'm saying that, okay, your f is somehow bounded above by 1 over x squared. And in this case, you can see that this kind of definition is always valid for your function f, right? Because if you take the integral, it will be arctangent. This function can be bounded above by some arctangent function, and arctangent function, arctangent n, well, as n goes to infinity is half pi. Arctangent minus n as n goes to infinity is minus half pi. Okay, so which means this kind of integral for this kind of function can be bounded above by pi. Okay, so then let's see some examples. Well, for what kind of function you could looks like this. For instance, your function looks like this. 1 over 1 plus x to the power n, right? This function is continuous, and when x is super big, it can be bounded above by x to the power 2, right? Because, well, your x to the power n is when n is greater or equal than 2, as when x becomes super big, which is much larger than 1, then of course x to the power n is much larger than x squared, so 1 over it is less than 1 over x squared. Okay? Or you may have some function looks like exponential. Okay? We know that exponential function decay faster than polynomial, which means if you use if you use a polynomial multiplied by this exponential function, and if you take x goes to infinity, then you get 0. Okay, you will always get 0. So which means this kind of function will be less or equal than some constant, some some constant and divide by 1 plus x squared, for sure. Actually, it will be less or equal than some constant divided by 1 plus x to the power n as n goes to infinity, or when n is super big. Okay, so exponential function, exponential decay function is also some function we are interested in. Okay, and we denote it by MR.
Oh wait, actually I have a question.
Of
Why
course.
why do we have to take it like as 2? I think that like if we take it like 1 plus any kind of like power,
That's
it's
a
still
very good point. That's a very, very good point. So this is something I'm going to say in a minute. Well, thank you for pointing out. So of course, you can see that when you take this kind of integral, you are only interested when n goes to infinity. What happens when n goes to infinity, right? So which means, well, if you have 1 over x squared, then it's arctangent, or it's 1 over n. As n goes to infinity, it is something positive. Well, it converges, right? But then, of course, why can't we have this fx is less or equal than some constant divided by 1 plus x to the power 1 plus epsilon for some epsilon which is greater than 0. Because we know that for this kind of function, you still get this kind of, this limit will be finite, right? Because for this kind of function, when x is super big, if you take, say, x from 1 to n, okay? If you take from 1 to n, this kind of a over 1 plus x to the power 1 plus epsilon dx. Although we don't know how to find the antiderivative of it, but we know that it's less or equal than 1 to n, maybe 2a divided by x to the power 1 plus epsilon dx, right? So this, you know how to find the antiderivative, is actually 2a times 1 minus, well, this would be 1 over 1 plus epsilon. I think it's 1 over epsilon x to the power minus epsilon with n to the power minus epsilon. I'm sorry. You plug in n. And this guy, if you take n goes to infinity, it will equals to 2a, which is something bounded about, right? So the limit exists. So which means it's still bounded. So of course, if you are interested in this kind of function, then your function will still satisfy this, the limit is still valid, right? And it seems that if we change this 2 to be 1 plus epsilon for any epsilon greater than 0, even epsilon equals to half, or epsilon equals to 0.1, 0.01, and so on, it's still okay. It seems still okay, nothing wrong. We still get some functions with the improper integral converge. The reason why we are interested in this kind of MR, the moderate decreasing function, is just because it's simple enough. Okay, we don't want to take this as 1 plus a half. We don't want to take it as 1.01 or 1.001. Although it seems somehow better, but then, then your function, you may have a lot of function for sure, but then that makes our argument slightly hard. For instance, when you try to argue whether it's a convergence or not, then you have to do some estimate. And then eventually you got the antiderivative looks very bad, not as good as this one, right? You know the antiderivative of this one is arctangent. Then, the proof will become a little bit more tedious. So which is why we simplify, the range of the functions we are discussing, but we make our argument easier. And soon you will see that we may make some even harder restriction on our function to make our theory looks elegant. And eventually you find that, okay, it seems that we only discuss this Fourier transform on this very, very special kind of function, which satisfy very, very seems impossible condition. But then you find that, although we have this kind of restriction on functions, well, it's in general, it's enough. In general, it is enough for us to use. Okay, this is something we are going to discuss maybe after an hour, which is so-called the Schwarz space, and why the Schwarz space or the Schwarz family, Schwarz function is a family of functions that enough for us to use. Okay, we will discuss it slightly later. But right now, you can see that the reason for us to define the modulus of the moderate decreasing function is simply because this kind of function is easy enough. It's easy enough for us to discuss. Okay? And then, now you see that we're trying to discuss some kind of function which decay very fast at infinity. Okay? And you will find that this, if you call this, as we mentioned before, if we call this, well, somehow like partial sum or partial integral of your function, then In forms a Cauchy sequence, right? Well, because In minus Im, well, if you nm big enough, can be written as you take the integral of x is greater or equal than n less or equal than m. Well, suppose m is greater than n. This then fx dx. Okay, and then it's less or equal than either you can use arctangent or you can even use well, when n is bigger than 1, we can say that it's less or equal than some constant, say 2a times 1 over x squared. Is greater or equal than n, less or equal than m dx. Okay, so this would be bounded about by 2a times 1 over n minus 1 over m. Okay, but well, minus 1 over m is something positive, so it's less or equal than 1 over n. Right, that's for sure. Then it turns to 0 if you take n to be big enough. So In forms a Cauchy sequence, so we know that at least for this family of functions, we have this limit as n goes to infinity minus n to n fx dx exists. Okay. So although it seems that we are kind of gets a very huge restriction on x, but as I mentioned before, you can somehow make it slightly less restricted, but then it doesn't matter. Okay, it just make our argument slightly tedious, nothing more than that. And well, and some basic property about MR, the moderate decreasing function, is MR forms a vector space, which means if you have two functions and they are both in MR, then the addition or the linear combination of these two functions still in MR. You can somehow do the addition and still get this function, still get a very quick decreasing function. Okay, finite linear combination. Okay, any question about this MR, the moderate decreasing function? Any question about it? Any question? Okay, so this would be some functions, the function space we are going to discuss or discuss about our transform. And let's see more propositions about this function space so that you will get a little bit more familiar with this kind of whole space integral or this kind of improper integral. Okay, the integral of function in MR satisfy the following properties. Okay, first, we know that if F and G in MR, which means they decrease fast enough, A, B, which are complex numbers, then, well, if you do a linear combination of F and G, it's actually, you can take it out. Well, that seems very trivial, right? But if you may still want to prove it just to get familiar with those kind of limit of the integral. Okay. And the second, this kind of integral, this whole space integral, is translation in. It has translation invariant. It is translation invariant. There's translation invariance of this kind of integral. Okay, so for any h in R, if you want to take this fx plus h dx, okay, then of course you can do a change of variable, but then you find that the upper and lower limit of the integral becomes infinity plus h and then minus infinity plus h. And you can imagine that that doesn't matter. So because minus infinity, formally minus infinity and infinity plus h is just infinity and minus infinity. So you still get this fx dx. You take the integral. Okay. And thirdly, if you try to do some dilations, okay? So if you try to multiply some constant to your function, well, here is you try to add some constant to your functions, do some translation. Well, it just doesn't change. There's infinity and minus infinity. But now, if you try to do some dilation of your functions, for any delta greater than 0, this delta is just some coefficient, some parameters. And then if you try to do a dilation of your x, this is so-called dilation, multiplied by some constant, then it's actually equals to 1 over delta. You take the integral and fx dx. Okay, this is also, I think, understandable. It's just like you make this delta x to be y, right? And then, so you should have 1 over delta and multiply by delta here. And then, well, your upper and lower limit will becomes from minus infinity times delta from plus to the plus infinity times delta, which shall we assume formula is still minus infinity to plus infinity. Okay? And 4, well, this is so-called the continuity of this kind of integration. Well, which is if you try to check what happens with this kind of functions, subtract your fx, okay, dx. It's more or less like you try to take the integral of the difference of this fx and fx plus h, okay? Then if you try to take h tends to 0, it will tends to 0 as h tends to 0, okay? In the future, if you learn this, so-called the real analysis, maybe the real analysis, you'll find that not even you have this kind of property. You can even find that in one-dimensional, it's actually if you divide h, then you still get something bounded. So which means this kind of thing can be bounded about by some constant times h. Okay, so which is stronger than this statement. Okay, so before we prove them rigorously, any question about these properties?
I have a question, but not about the properties.
Okay, what's
Can you give an explicit definition of the space and R? I mean, it's confused by it.
Of course. Yes. MR is all the functions. MR is all the functions we'll define on R, which is moderate decrease, which means a function f in MR, if it is continuous and it satisfies this inequality for some constant a. Okay, so which means it will decrease at infinity, decrease very fast.
Okay.
Yeah, this is so-called some functions decrease very fast. If we want to say some functions decrease very fast, and then we choose 1 over x squared. That's our criteria to say that it decreases very fast. Okay. So any other question about these propositions of this, this whole space integral?
Are we talking on the real space, like the function are real valued?
Exactly. Everything. Well, the function may not be real valued, but it will define on only R. Okay, so you cannot plug in some complex number to your function.
But Fourier, like for the Fourier series of include many complex numbers in there.
Yes, but as I said, your function cannot evaluate as some complex numbers as variable, but it could be complex valued.
Oh, do you mean that the value of fx can be some complex numbers?
Yes, for instance, because we are interested in this kind of function, right? Eventually, we want to define those kind of Fourier transform. So, which means your function may be something else, right? Your function could be something like x 1 over x squared 1 plus I times say 2 over 2 plus x to the 4th. Okay, this could be your function. And then if your function is complex valued, it doesn't matter, because it's just to say that, okay, you can still understand it as a real value function, because it's just a function contains 2 components, right? And when you're trying to do any estimate, you can just do that component by component. It doesn't really hurt anything. So as long as you know everything about the real valued function, you are able to understand everything about the complex value function, at least in our theory. Okay, so it doesn't matter. Okay. Any other question? Okay, so let's try to prove it. Let's try to prove it. It seems that these propositions are very intuitive, okay? But we still want to prove them because, well, I just want to make sure that you kind of get familiar with those kind of whole space improper integral, okay? Just to make sure that you can handle it, and just to make sure that you are able to do whatever we want about this, about this kind of analysis estimate about integral, okay? So, but still for one, it's trivial, so I don't really want to do it because you can see that the limit, you can split it into two parts, and then you can see that, okay, it must equal to that. This is kind of trivial, okay? Let's start from 2. For 2, well, you want to show that from minus n to n, fx plus h dx minus from minus n to n fx dx tends to 0 as n goes to infinity, right? You want to show this equals to this. That simply means fx plus h minus fx, if you take the integral from minus infinity to infinity, it should equals to 0. Then by our definition, it's just the same as where you take this kind of difference and then take the integral, this partial integral, and then you take the limit as n goes to infinity, you should get 0. This is what we want to show. Okay? That clear? But then, well, this is not so hard, right? This is something we are able to handle because what's this? It's just it is nothing but the integral. We can do the change of variable because it's finite domain integral. So it's minus n plus h to n plus h fx dx minus from minus n to n fx dx. Right? So you take the integral from minus n to n. But this one is you take the integral from minus n plus h to n plus h. So that means if you take the subtraction, you only take the integral from here to here, right? So it's an integral from minus n plus, well, I mean, this should be minus h, I'm sorry. Is that minus h or plus h? It's minus h. I think it's minus h, right? When x is minus n, oh, plus h.
But you draw the wrong.
Yeah, I showed the wrong picture. You are right. Yeah, but it's still this part and plus this part. Okay, so it's minus n plus h. Well, from minus n to minus n plus h, fx dx plus from n to n plus h, fx dx. Okay, now you want it tends to 0, so let's say how we can do any estimate of it. If we can estimate it by something tends to 0, then we know that it tends to 0. Okay, so it's less or equal than we can bring this absolute value inside minus n plus h fx dx plus n to n plus h fx dx with absolute value. Okay, so it's less or equal than from minus n to minus n plus h fx dx plus n to n plus h fx dx. Okay, we just try to move our absolute value inside of our integral. And this one, okay, we are able to, for this one, we are able to use some decay condition of fx in order to show it is somehow will tends to 0. Okay, so this would be less or equal than a divided by, well, from here to here, the absolute value of x will have maximum like n. N minus h. Your function will be less or equal than 1 over 1 plus x squared, right? So 1 over 1 plus x squared, when x is inside of this domain, inside of this interval, it will take the maximum value when x equals to this one, right? because the value of your x is minimal at this moment. So the denominator will become minimal at this moment. So it's less or equal than a over 1 plus n minus h squared.
Should we multiply out small h over here because it's integration?
And multiply the integral from minus n to minus n plus h 1 dx. Okay, so your fx is less or equal than this number. Plus this fx is less or equal than a over 1 plus n squared, right? Well, this one is smaller than this one, so it's well, fx is less or equal than 1 over a over 1 plus n squared. You still get n to n plus h 1 dx. Okay, so this is less or equal than a divided by 1 plus n minus h squared plus times h plus a times h divided by 1 plus n squared. So you can see that it tends to 0 as n goes to infinity. You can use epsilon delta language to say it, okay, but you can also see it very clear under this expression. For fixed h, it will tend to 0. Okay, any question? Then for 3, it's actually the same thing as this one, okay? So I will skip it. It's similar to 2 because it's nothing but, again, a change of variable. And you just change the upper and lower limit, and then for fixed delta, as n goes to infinity, you find that, okay, nothing need to argue too much. It's still like 1 over n squared and something like that, and it will tend to 0. Okay? So I'll not prove 3, but for 4, let's see how to prove 4, which is somehow different. Somehow different, which is the integral from minus infinity to infinity fx plus h minus fx. Well, we know that it will be very small because your function is continuous. But then you take this integral from minus infinity to infinity. It is on everywhere. You take the integral. We want to show that it tends to 0 as well. Okay? So which means you have a very, very small things, small values everywhere, and then you take the summation, it's still very small and tends to 0. This is something very interesting, right? Any question? So let's try to prove it. Y tends to 0. Here we must be careful about the argument and well, about especially on different order of you taking the limit. You can see that this kind of thing is you first take the limit as the improper integral, okay? Then you take the limit as h tends to 0. So if we want to prove that, that's well, we want to show that for any epsilon, this, well, you can choose some delta so that h, well, little h is less than delta. You will have this whole integral less than epsilon, okay? So for any given epsilon, we want to find some delta neighborhood of your h. So let's try to find the neighborhood of h. What would be the requirement for neighborhood of h? And eventually we make a summary and see that, okay, we can choose delta to be something, something, and then, okay, it will work. Okay, so first, let's assume that your h is less than 1 to argue it, well, easily. Because you are going to take the limit as n goes to infinity, okay? So, well, if h is less than 1, then what we can say is, well, there exists some n, okay? So that if you take the limit, well, if you take for all the x, which is greater or equal than n, fx dx. Okay, so which means if you are only interested on this far field of your integral, which is this kind of integral is like you take from minus infinity to infinity. But now, if we are only interested about, well, from some big number to infinity and some big negative number to minus infinity, then this part could be very small. Because we know that this kind of integral would be something converge, right? So the tail of this integral, which means from n to infinity of this integral, will be very small. Okay, so we can choose such kind of n so that this kind of integral is less than some small number, so that we can somehow ignore this part. Okay, ignore the far field part and concentrate on this bounded part from minus n to n. Okay, so you can see that this kind of integral can always be decomposed into two parts. One part is, well, this integral which are very close to the infinity. And another part is this integral which are not very close to the infinity, which is something bounded. Okay, so if we want to show this, we will discuss them separately. So if you have this kind of epsilon, then we must exist some n such that this kind of thing is very small. The tail of this integral is very small. Meanwhile, if you have fx plus h dx, it's also very small. Right? Which is why we want this, well, h is less than 1, so that we still get this kind of decay property, and we still get it's still very small. Okay, otherwise if h is very big, then, well, it might not be true because maybe you have some negative number, but plus something very big, then it might be very small. Okay, so we want this h to be not very small so that it will not hurt n. It will not hurt the tail of your integral. Okay, any question? This is actually a very standard argument in analysis, which is when you have this kind of integral on whole space, then bounded domain would be interested for us. And well, far field would also be interested. But the interesting point of these two parts might be different. Okay? So now we can only discuss about this fx plus h minus fx on some small domain or bounded domain. Okay? Then for such n now is a fixed number, because as long as you give me this function, I can find such n. As long as you give me this function, you give me this epsilon, I can find such n. And n is a fixed number. For instance, if I give you this function, it could be 1,000 or 1 million. Okay, it doesn't depend on h. It doesn't depend on h, but it only depends on epsilon. Okay, for such n, well, there exists some h. Okay, because you know that fx is continuous say minus n minus 1 to n plus 1, that means fx is so-called uniform continuous. This finite interval. Okay, I hope you still remember what is uniform continuous. Okay, it just means that on this interval, whatever epsilon you gave me, I can find a uniform delta such that as long as your fx minus fy, x minus y is less than delta, then fx minus fy is less than epsilon. Okay, such that, well, if you take the supremum of all the x is less or equal than n, you have fx plus h minus fx is less than, say, epsilon over, well, maybe I should say, well, I may need to choose it later. Let's say it's less than epsilon over 2n plus 2. Okay? N is a fixed number. And of course, we can choose h to be small enough such that this fx plus h minus fx is always less or equal than epsilon epsilon over 2n plus 2. Okay? Is that clear? Because your fx is uniform continuous on this interval. Maybe I should multiply 2. You will see why I need multiply 2 here, but it doesn't matter at the very beginning. That okay?
Sorry, but like, where did we mention that fx is uniformly continuous?
Well, maybe I should mention it here again. So for uniform continuous,
Sorry, I didn't mean the definition. I mean like just for the proof part. When did we say that the f in this proof is uniformly continuous?
f is in MR, right? So f is continuous by definition. Don't forget, or MR, the moderate decreasing function, is not only have this condition on decreasing, right? We also need it at least to be continuous. If it is too rough, then we don't want it. Okay? And f is continuous on a closed bounded domain. Closed bounded domain, like an interval, closed interval, then the conclusion is f is uniform continuous on this interval. Okay? Implies uniform continuous. This is a proposition about the continuous and uniform continuous. A function is continuous on AB. That implies this function is uniform continuous on AB. Okay? So we have this function is uniform continuous, so we can choose h to be small enough, and so that it's very small. Okay? I just write it here because we will use this kind of formation in the future, but you can just think that it's very small. Okay? Uniformly. So this means the integral from minus infinity to infinity fx plus h minus fx dx is equals to ux is greater or equal than n. Okay? Fx plus h minus fx dx plus ux is smaller than n. Fx plus h minus fx dx. We can separate your integral into basically two parts. One part, your x is not very big. Your x is not very big. One part, your x is very big. Okay? Then it is less or equal than, for the big part, we know that it's less or equal than the integral of fx plus h plus the integral of the fx. And both of them are smaller than epsilon over 4. So the first part is less or equal than, well, epsilon over 2. Okay, so it's epsilon over 4 plus epsilon over 4. Okay, is that clear? And for the last part, for the second part, you know that uniformly, when x is less than n, this is less or equal than epsilon over 2 times 2m plus 2. Okay, and you have to multiply by x is less than n. Time, well, you take the integral of 1. I think that I make it slightly, well, smaller, but it doesn't matter. So it's less or equal than epsilon over 4 plus epsilon over 4 plus epsilon over 2, which equals to epsilon. Okay. So you might be, as I mentioned before, as a beginner, you may try to argue this kind of thing again with the explicit definition of this limit. Okay, which means you can say that, okay, when you take this m from, we'll take the integral from minus m to m, and you take the limit as m goes to infinity, well, and in this process, you still get it's very small. Okay. But in general, what we are going to discuss in the future are always this kind of notation. If x is super big, if x is super small, and x super big, x super small, you take the addition of these two, it will gives you the whole integral. Okay. So any question about this proof? Any question? So we've done it. Okay, we have proved these several properties about the integral, this improper integral on the whole real line. Okay, and it seems that whatever we want to do formally is always valid on this integral. Okay, now we are able to define the Fourier transform of a function. Okay, let's try to go through the definition of Fourier transform. Okay, then well, the definition is just as I just showed you. Now, if f is in this moderate decreasing function, it's a moderate decrease function, we define is Fourier transform as, well, for f, well, c in R by this f hat of c is equals to the integral from minus infinity to infinity fx times e to the minus 2 pi I x c dx. Okay. This is the definition of Fourier transform, and maybe I should write the Fourier coefficient, the definition of Fourier coefficient here to compare with. Okay, it's 1 over 2 pi from minus pi to pi. Here, the integral domain is slightly changed. The integral domain has changed. Okay, but this inner part doesn't change at all. It's e to the minus inx dx. But these functions are also different. This function must be periodic of period, say, 2 pi. Okay, but this function is just something very nice, but decrease, so that it's valid. Okay. Well, this is definition of Fourier transform. It seems not very hard, right? As long as you have this, well, this integral makes sense, then you define the Fourier transform to be this kind of formation. And let me write one observation of this thing. First, well, we can see that this f hat of c is bounded above. Okay. that true? Why f hat of c as a new function is bounded above? Why it is bounded above? Anybody give me an answer? Why this kind of thing is bounded above?
Because it's well, if x goes too big, then basically the terms get smaller and smaller, and yeah. So, or wait, also we kind of did a property of it that. Wait, give me a second.
So, well, let's try to compare with this kind of thing, okay? This Fourier coefficient. Did we mention that the Fourier coefficient of an integrable function is bounded above? If yes, how did we prove it? How did we prove it? Why the Fourier coefficient of an integrable function is bounded above? Any idea?
Well, intuitively, because it has e in the power of I and x, and when n and x both go big, then basically it gets very close to 0.
Mm-hmm. Well, so what's the difference between this function and this function? Or what's the difference between your fx, you know f is in,
I
and
think
this?
we can. We can use the properties of f is in MR. And we write 1 plus x squared multiplied by e to the 2 pi ix something, and write e blah 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 into cosine and sine, and we can find the bound, I think.
Yeah, I think you got the right idea. So basically, this part on your integration, it will not provide you any growth of your function. Why is that? It's just because if you take the norm of it, the norm of this part equals to 1, right? It always equals to 1. So which means this kind of integral is nothing but some oscillation functions. It's just some oscillation from -1 to 1. So sometimes...
I think that when we did Fourier coefficients, we said that fx should be bounded because it's an integrable function.
Yes.
And then we basically got like say m multiplied by 2 pi divided by 2 pi. But here we cannot do that because like we have from -infinity to infinity. So even if fx is bounded, it doesn't help much.
It doesn't help if your f is bounded, but your f now is in moderate decreasing function, right?
Oh yeah, then we can just we can still bound it by this thing, and we can bound it by an integral of that 1 divided by 1 plus x squared stuff, and so yeah, okay.
The reason you said right. The reason you can do that is simply because this part, which is some ugly part, although it looks like exponential function, but the norm of this part is always 1. So sometimes we call this kind of integral to be the oscillation, the oscillate integral, or this I think people call this oscillate integral if you have some kind of other things here to make it more complicated. So why is bounded above? It's simply because if you want to take the bound try to estimate the bound of it, is equals to or less or equals to from minus infinity to infinity, you take F's value inside, right? Or you take the norm inside. And of course, it's less or equal than, or is actually equals to from minus infinity to infinity fx dx, right? And your fx is less or equal than a over 1 plus x squared. So it's less than infinity. Okay, similar thing here. Similar thing happens here because your fx is bounded above, it's periodic, and then this part will Q if you take that value inside. So it's bounded above. Okay, so if you take the norm, it basically kills every oscillation of your integration. Okay, this is the idea. Is that okay? Any question? And another observation is, well, the problem, well, yeah, you can actually show that this f hat of c, just like f hat of n, it tends to 0 as c tends to 0. Okay, it tends to 0 as n goes to infinity. Infinity. Okay, this one we call it Riemann-Lebesgue lemma. This one you will have to prove it. This is one of your homework problem. So which means the f hat c, just as fx, it also has some kind of decay. For fx, it has a very fast decay, right? It decays like 1 over x squared. And for this one, it also has some kind of decay. However, f hat of c may not be in this space, which means it may not decay very fast. Okay, I think this is another homework problem I'm going to assign you, which is something at this moment it's just the same that, okay, that's fine, because you can see that this kind of thing is also not as nice as we want, right? That's for sure. We know that only if your f is second differentiable, right? It's a second continuously differentiable. Your f hat n will have some decay. It is less or equal than 1 over n squared. So there is no reason for us to expect this, the Fourier transform of a function to decay very fast. If you do not have some kind of smoothness of your function itself, right? But this also gives us some kind of, well, problems when we try to think about this kind of functions. Because if you take the Fourier transform of a function, it is moderate decreasing, but the Fourier transform may not be moderate decrease. This is not as good as what we want. You will see why I'm saying that in a moment. The intuition here is, well, the faster f hat of c decrease, the smoother f must be. Okay, it's just like the Fourier coefficient. Well, if you do not have some very good smoothness of your function, then the Fourier coefficient may not decrease very fast. If you do not have some very good smoothness of your function, then the Fourier transform may not decrease very fast. Okay, so in this sense, maybe if we really want that, or as we mentioned before, The reason why we want this Fourier transform of a function is still something very smooth is simply because for a Fourier transform of a function, we want to do the Fourier transform again. And as I mentioned before, if you do the Fourier transform 4 times of a function, you can try to, well, we will prove that in the future, okay? If you try to do the Fourier transform 4 times, then you can get back to your function, okay? So which means if you want to get back to your function, recover your function by the Fourier transform of your function, which is something we really want, right? Because well, if we only know what is a Fourier transform of the function looks like, we don't really know what is the functions looks like. So that even if we can use a Fourier transform to solve some PDE, right? We can transfer your function and then makes your PDE to some ODE or even algebraic equation. But then we only solve the Fourier transform of your function, not more than that. We still want it back. We still want our original function or original solution, right? So which means we may want to take more than one Fourier transform of your function, or at least to take the so-called inverse Fourier transform, which is you take the Fourier transform 3 times to your Fourier transform of your function. But if this function is not good enough, if this function is not in this modulus of decreasing function, then we cannot really do the Fourier transform, right? Because we don't really know whether the Fourier transform exists or not. So in this case, maybe we should try to build some other kind of a space, such that if you have a function on this space and you take the Fourier transform, you still get a function in this space. So you can continuously taking the Fourier transform, so that we can take this kind of inverse Fourier transform to get back to your function, right? So let's see, if we want to build this kind of space, what do we need? Okay, as we mentioned, this f hat, we don't know it, right? It only decreases to 0. So if, as we mentioned, if we want to decrease a little bit faster, like 1 over c squared, then by the intuition we get from the Fourier coefficient, we want our function to be twice differentiable, right? So maybe if we try to modify our function space, what we want is, okay, your function must decrease as 1 over x squared. Moreover, your function must be twice differentiable, right? Okay, in that case, you can see that, okay, at least the Fourier transform may be decay as 1 over x squared, well, 1 over c squared, right? It may have this decay property. But then we change our space a little bit. It changed to be, okay, your space are all these functions such that the function has some decay. And moreover, it's not only continuous, but also, well, it's not only continuous, but also smooth. It's twice differentiable. So then we will need that, okay, this function must be twice differentiable. Is it twice differentiable? It may not be. If you try to look at it, you'll find that it may not be twice differentiable. What you need is something else. You may need something a little bit more than the condition you previously described for your function. If you want this function, the Fourier transform of your function, to be twice differentiable. Okay, so in this case, what we want is to add more restriction on this function space, the module, the MR, so that we can get back to our functions. The Fourier transform of your functions is still on this space. So if you add the restriction again and again and again, then eventually you'll find that, okay, what you really want, your space, the function space, should be so-called the Schwarz function or the Schwarz space. The Schwarz function or the Schwarz space on R consists of set of all the functions which are infinite differentiable, okay, which is sometimes we call it smooth. Oh, indefinitely differentiable, which means you can differentiate infinite many times, you still get something, well, something differentiable, okay? F, so that the following, well, let's say F and all the derivative F prime, F double prime, until F to the, well, else prime, let's say this is else prime, okay, are so-called repeatedly decay. What's the meaning of repeatedly decaying? It just says that it decays very, very, very fast. How fast it is? Faster, it is faster than any polynomial, okay? Which is the supremum of x in R, x to the power k of this derivative, the else derivative of this function is less than infinity. It's bounded for any k and l which are greater or equal than 0. Okay, so which means your function decay whatever faster than arbitrary polynomial. Any polynomial, you multiply this function, it will not be something infinite. It's just something bounded above. Okay, it's just like an exponential function. But more.
Oh, yeah, I just had a little question. So, like,
Sure.
I don't really know a lot of functions which are indefinitely differentiable. Like we know polynomials, we know sinuses, and we know exponents.
Yeah,
like
exactly. It's very hard to imagine, okay, what kind of function would satisfy this kind of condition? First, you can take arbitrary well, that derivative, right? And whatever derivative you take, it will still be something decay very, very fast, right? So what kind of function we are discussing? It seems that we are discussing some empty set. So, well, this is the definition of Schwarz space, but what would be the example for what kind of functions we are really discussing? I think I will leave it here and we will discuss in 10 minutes. Okay, let's have a short break. We will resume at 29. Okay, you can think about what kind of function, well, can we write it down so that it satisfies this rapidly decaying property?
And it has to be for x or for x going to infinity. It has to be for all x, right?
It has to be for all x. And
Oh, no.
but it's the same as when x goes to infinity, it is bounded above, right? Because when, well, your f is continuous and your f is very nice. So let's continue. You can see that we define something, but you don't have any functions in your mind that looks somehow close to this kind of functions, right? And Lang Chen gives us an example, and it seems that e to the minus x looks a very good candidate. However, unfortunately, it is not, because we know that e to the minus x, it is very good when x tends to infinity. And if you take derivative, it is also very good when x goes to infinity. It decays very fast. It's faster than any polynomial, right? You know that. Any x to the power k multiply this e to the minus x will tend to 0 as x goes to infinity. However, when x goes to plus infinity, it will increase. So of course, if you take times x to it, then it will goes to infinity as well, as x goes to minus infinity. So this may not be a very good example. Then you may think, okay, the main reason is you only goes to infinity when x goes to infinity, right? Then if you want it also goes to 0 when x goes to minus infinity, then what if we take the function like this, which is the absolute value of x? That looks very nice. At least this function, if you try to look at it, it decays fast enough. However, the only problem now is you have a point that is not differentiable. You have a cusp, or I think this is not a cusp, this is a corner of your function, right? So at this point, when x equals to 0, it's not differentiable. This function is not differentiable. So again, maybe we need more, well, calculation.
Can we try maybe like 1 divided by, say, 2 like modulo n multiplied by sinus or something like that? Because like sinus is already bounded, and if it's going to have a coefficient of like 1 divided by 2 in, like, you know, modulo n, then it also may not have this kind of not being able to differentiate at this point, because it's going to be 0 anyway there. So maybe it can work.
But the problem is, then where did you get the decay of such function?
From the
Something
1 divided
decay.
by 2 in the power of something stuff.
Well, but then that function may not be continuous, right? Looks very ugly.
Wait, why would it be continuous though?
Well, why is it
Why?
continuous? Well, what is a function? Sine and x something, right?
No, sine x.
Sine x.
Sine x, and it has to be multiplied by a coefficient like 1 divided by 2. Yeah, like 2 in the power of modulo n.
X modulo n.
Like how do you call it? Like the absolute value of n.
2 to the power n.
Yeah, but n in a like absolute. Yeah, okay. So would that work?
But n is n a number?
Oh yeah. Well, we can do it like x.
Well, okay. So it's 2 to the power x sine x, right? But
Something
this
like
is smooth, right?
Oh.
It's just like this, right?
Yeah, but I think maybe we can still differentiate because at this point it's going to be
I think
because
you're right.
sine is an odd function, so and also there are going to be zeros there, so
I think you are right. I think you are right. This kind of function, well, the only point that it may not be continuous or differentiable is this point, right? Because you have absolute value. But then this sine function may somehow be 0 at that point. So maybe it's smooth. So I think you probably will be right. And I think the idea of you is very good, because you try to smooth this point, right? You try to do some survey about this point and make your function smooth at this point. Of course, if it is only on the graph, it is very easy to make it smooth, right? You just draw it somehow smooth here. But then the problem is, well, if you have a function, then how can you make it smoother at this x equals to 0 point? I think your idea is a very good idea, which is you try to cut it. You try to cut it and make it somehow smooth, okay? However, this is a very good idea, but we still need to check it, and it's not very easy to check. There is an easier way, okay? There is a shortcut to make this idea valid, which is the absolute value of x is not smooth, right? But we know some function which is smooth, and it has same properties to infinity and to minus infinity, right?
X squared.
Yes, e to the minus x squared. The only problem for this function is if you take the derivative, it seems that you will have some polynomial multiplying it in front. So that might be a problem. However, if you look at it, you'll find that the only thing that will be different if you take the derivative of this function to the original function is just you multiply by some polynomial, right? And we know that this kind of function, it decays faster than polynomial, right? And this function, eventually you can show that, okay, so even though you multiply some polynomial after you take derivative, but still whatever other polynomial, additional polynomial you multiply it, you still get something decay very fast because you already got something decay very fast, much faster than any polynomial, right? It's in ISR, and this we call it, we denote it as Schwartz space as SR. Okay, very fancy S. Okay, maybe I should say write it very fancy. The Schwartz space. And this function is in the Schwartz space. Moreover, this function is a very famous function. It's so-called the Gaussian. Okay, it's very, very important in the, well, probability or stochastic analysis. And it's very important in some, well, engineer area, okay, areas of engineer. And well, this function, it looks like exactly what we want. It has some concentration here, and it has some, well, decay at infinity. Okay, so this is an example of, well, Schwartz space function or Schwartz function. Okay, and of course, since this is an example, then if you multiply any polynomial to it, it's also in this Schwartz space. Okay, P is a polynomial. And if you try to do some dilation, multiply by A, for A positive, it's also on SR. Okay? Is it very, well, of course, if you already have this function, then of course, if you try to multiply by some polynomials or try to do some dilation, it is still in SR. But it seems that this one is the easiest one that seems on this space. It seems that it's the only way that we can imagine, well, what does this space formed by, right? It seems that if we want to find some non-trivial functions in this space, it must be somehow looks like this. At least on the graph, it should look like this, right? Even if you try to make this kind of function, the graph should also look like this. It will decay exponentially and have some, will have something not so bad at the origin, right? Any other function? Anybody can guess? Can make a guess for what kind of function? We need to write the expression of this function, but any other kind of function? Maybe on this space. Well, so I will tell you the reason why we can only study this very, very weird space with a very strong restriction on this space. Here is a key reason. We study this space, of course, not only study this function, right? This is only one example, although it's very important, it's so-called Gaussian, and you will see it anywhere, but it's still just one function, okay? The reason we are interested in this space, and this space does make sense, is simply because all these kind of function are in this space, okay? If we have a function, and this function is so-called C infinity function, which means it's smooth, or you can take arbitrary derivative to this function, okay? And Sometimes we call it C0 infinity, or sometimes we call it CC infinity. Means this function has compact support. Well, what's the meaning of the support of a function? The support of the function just means the function is not equals to 0 only on, on the support. Okay, all the point such that this function is not 0. Compact support simply means this function only non-zero on some finite interval. Okay, on some finite interval. Then f is in this Schwarz space. For example, although I don't know how to write it down, but if you have a function which is 0 here and 0 here, but not 0 in between, and this function is, well, it's differentiable anywhere, then this function, of course, is in Schwarz space. Okay? So all these functions, which is smooth, infinite differentiable, and compactly support, is on this Schwarz space. Right? Why is that?
Can I have a question? So
Sure.
the notation C 0 infinity, does the 0 and infinity have any meaning?
No, this infinity just means, for instance, C2, it means twice differentiable. This function is twice differentiable. But here, this 0 or C just means, well, it's compactly support. Okay, it's a special notation. You cannot say C1 infinity. That doesn't make sense. Okay.
Okay.
Okay. So this C just means compact. Okay. This 0 just means, okay, it has 0 so-called boundary condition, and the boundary for R is just infinity. Okay, we can try to imagine it that way. Okay, so you can see why I say the smooth function with compact support is in this Schwarz space. It's simply because, well, it's compactly support. Then of course the derivative is also compactly support, because otherwise the derivative is just a 0, right? You have 0 everywhere else is just a 0, the derivative is just a 0, right? So which means all the derivative of such kind of function, CC infinity, such kind of function, are compactly support. And if your function is smooth and compactly support, that means it's continuous and compactly support, then of course, you multiply any function x to some power, it's still continuous, right? It's still continuous. This function is continuous, and this function is defined only on a finite interval, so it, by Fermat's theorems, is bounded about, right? So this condition will automatically satisfy if you have this function to be finitely support or compactly supported. Okay? Is that clear?
Sorry, could you explain the meaning of compactly support again?
Compactly support. Maybe, well, this may be somehow confused. So let's say, let's make it this way. So, well, fx for x, for those fx not equals to 0, this is so-called the support of your function. This is the support of a function, okay? And then compactly supported means this support of the function is a compact set. In R, that simply means it's inside some finite interval, and it's actually closed and bounded, okay? It's inside of some interval. Okay. So Compactly supported means there exists AB such that A is a subset of AB, or A is bounded and closed. At least it's bounded. Okay?
Okay, thank you.
I think in your 308, you already learned what is compact, or at least you know what's the meaning of bounded and closed interval.
Yes, we learned that.
Yes. So compact support just means that the support, which is all the point that your function does not equals to 0, has some, well, it's a bounded set. Okay? It will not go to infinity. It's just like this kind of picture. Other than this part, your function equals to 0 identically. Okay? So this set, smooth function with compactly support is a subset of our Schwarz function. Okay? And you will see that in the future, maybe not in our course, you will see that all the functions can be approximated by a family of functions with which is smooth and with compact support. Okay? Well, you can imagine this must be true, right? For any function you gave me, then what we can do is we can somehow cut it, right? And then somehow make it very smooth here. And this, if we extend or cut off, then we will get a closer and closer function to approximate your function, your original function, right? In some sense, of course, in some sense. So this kind of thing, this kind of function space is, although you cannot really write down any function that in this space, but it is, in some sense, dense among almost every function space. Okay? And one of the homework problem you will have this week is, well, you will be asked to find such kind of function. For instance, how you can find a function such that looks like this, like a table, okay? And it is also smooth. How you can make a function looks like this. This would be a homework problem. How to write such function. Okay. I think this would be useful in the future, no matter whether you learn analysis or not. But at least if you want to learn analysis, then this would be the most important family of functions. Okay? Any question? Any question? Okay. So we can see that our Schwarz space, although it looks like something very unusual because we cannot really find any elementary function, almost elementary function that inside of this space other than the Gaussian, right? But it's still very useful and it's not an empty set. There are a lot of very interesting functions on this space. Although we cannot write it down, or although we write it down, then it will be really complicated. But we're still interested in this family of functions. It still makes sense. So let's try to find more properties on it and see what we can do this space by our Fourier transform. Okay. Well, for instance, there is a proposition, say, well, if F is in this Schwarz space, it's a vector space, which means if you have two functions, a linear combination of these two functions are also in this space. Okay, and if F is in SR, then what we can say is the derivative is also in SR. And X times F is also in SR. Okay. Now, let's see what we can do about, instead of the moderate decreasing function, but functions on SR, about our Fourier transform. Okay. For functions in this SR, of course, we can define the Fourier transform because SR is actually a subspace of MR. Okay. So if F is in SR, what we will have is, well, let's say you have an Fx, then the Fourier transform, this arrow just means the corresponding Fourier transform of this function is f hat of c. Okay. Then we will have the following propositions. Fx plus h will have the Fourier transform as you do a translation on variables on this function. Then on Fourier transform, it will becomes a multiplication e to the 2 pi I x c. Okay, for any h in R. Secondly, it is actually doable, it is actually a duality of the Fourier transform and this function. By the way, sometimes we call this function is in the phase space or the physical space, and the Fourier transform of this function is on a frequency space.
Professor, I think the power should be h instead of x.
Yeah, thank you. Yeah, thank you. And this is so-called the Fourier transform of this function. It lives on the frequency space. And this is something relevant to ECE, the electronic engineer. Well, double E, I think. Yeah. And this is very, it's just a notation. And if you are interested in this part, you will see why this is so-called physical space or phase space. This is so-called the frequency space. It's relevant to the signal. Okay, very important application of this Fourier transform. And if you have your function multiply by those kind of thing, e to the minus 2 pi I x h, then if you do the Fourier transform, it is c plus h for h in R. Okay, so it's kind of has some kind of duality, which looks much better than those Fourier coefficient or Fourier sequence. Actually, they are the same, but they're just not as good as this one. Okay. And third one, well, if you do a dilation on this function space or on this phase space, then your Fourier transform will becomes 1 over delta, the Fourier transform of 1 over delta times c. Okay, and c delta is greater than 0. Okay, so it's just some kind of similar thing, but with well, here you have delta, here you have delta inverse. Okay, dilation corresponding to the dilation, phase space dilation corresponding to the phase space, well, the frequency space dilation. And the fourth one, which is the most important one, if you take derivative of your function, the corresponding Fourier transform would be 2 pi I c times f hat of c. Okay, so it's a multiplication of c instead of the derivative. So it can transfer the derivative to a multiplication. Okay, here it can translate this kind of dilation to this multiplication of exponential stuff. But here, if you take the derivative, it's still a multiplication. And lastly, similar things happens as you have this derivative on the phase space, you have multiplication on the, well, on this frequency space. But if you have the derivative on frequency space, this is something we are able to do. because it's a new function. Then on the physical space or the phase space, what you have is minus 2 pi ix. Still a multiplication. Okay, which is why I say that this is more or less like a duality. You can go from function to the Fourier transform. You can also go from Fourier transform to the function. Okay. It's almost like the Fourier transform. If you take the Fourier transform again, you'll get back to your function. But we know that it's not true. You will need to take more Fourier transform instead of that. Okay. Any question about this proposition? Any question? Well, the proof of this kind of propositions are, well, I should say, are very easy. Simply because we choose some functions in the Schwarz space. I'm sorry. We choose some functions in the Schwarz space, and it makes all our argument about the convergence easy enough. Okay? Let's try to prove that. So for the first one, it almost looks like some algebra problem. Okay, you have fx plus h, you take the Fourier transform of it. Then it is minus infinity to infinity, fx plus h, right? E to the minus 2 pi ix c dx. Okay, you just need to do a change of variable. And we know that if you do the change of variable, as long as this part is a good function, you still get a good function. So you don't need to worry about it. Formally, you can do that. From minus infinity to infinity, it doesn't change. You still get fx. But here, you should change x to be x minus h. C dx. Okay? So now it is from minus infinity to infinity fx e to the minus 2 pi I x c times e to the minus h times minus 2 pi I h c dx. This part doesn't depend on x, so you can bring it out. E to the 2 pi I h c, you take this integral of fx. Okay, which is what we want. You can see that, not very hard, right? It's just to bring out do some algebra. The second one is similar. Your fx times e to the minus 2 pi I xh, you take the Fourier transform, is from minus infinity to infinity, fx times e to the minus 2 pi I xh times e to the minus 2 pi I xc dx. Okay, and this will be minus infinity to infinity fx. Well, these two have everything almost the same, e to the minus 2 pi I x times h plus c dx. So it's f hat, well, c plus h. Okay, so you don't do anything, just this kind of calculation. And the third one, well, you have f delta x, you take the Fourier transform, then it is from minus infinity to infinity, f delta x e to the 2 pi minus 2 pi I x c dx. Then again, we want to do the change of variable. Delta x equals to, say, u. Then you should have 1 over delta in front of it. From minus infinity to infinity, fx, well, e now is x. You change x to be x over delta. Minus 2 pi I x over delta c dx. So it is 1 over delta. You move this delta to this c. So it's f hat evaluate at 1 over delta c. Okay. That clear? Yeah, clear? I think it's, well, it's just some, well, easy calculation, change of variable. Hope it's fine. Now,
Yep, looks good.
okay, good. Now we want to show the derivative stuff, right? Well, if you want to show the derivative stuff, then probably we have to do it slightly slower, because for derivative stuff, you know that you will want to use integration by part, just as what we did before, right? For the Fourier coefficient. We want to do the change of variable, we want to do the integration by part, so maybe we do not really want to do those kind of take the integral from minus infinity to infinity. But instead, let's take the integral from minus n to n, and then eventually we take the limit, okay? So it's f prime of x of e to the minus 2 pi I xc dc. When n goes to infinity, it is the Fourier transform of f prime, okay? And let's see what it is. This would be fx e to the minus 2 pi I xc evaluate from minus n to n, okay? Plus, if you do the change, well, integration by part, then it's plus 2 pi I xc, right? Take the integral from minus n to n, and the fx will e to the minus 2 pi I xc dx. Okay? Then you can see that when n goes to infinity, we can see this first term just disappear because fx decays super fast, right? So it will disappear very soon. So what we get is, okay, f prime hat is equals to 2 pi I c f hat c. Okay, is that clear? Well, lastly, we want to show this kind of thing. Yes, if we really show that the Fourier transform, if you take this 4 times, then you should go back to it. Or if we already find what is the Fourier inverse Fourier transform, then probably this will be very easy. But at this moment, we don't really know how to take this kind of calculation. Then, for this part, let's consider this formation. Okay. F hat c plus h minus f hat of c divided by h. You can see that when h tends to 0, this will tend to the derivative of f hat. And minus will the Fourier transform of minus 2 pi I x f x of this. Okay. If we can show that when h tends to 0, this formation tends to 0, then we are done, right? We only need to show this. Okay, so is it tends to 0? Yes, it is. Let's try to write it carefully and see what we can get. It is. You take the integral from minus infinity to infinity. At this moment, we don't see why we cannot take this, this thing. Well, let's see. If we have some problem, maybe we can cut it and try to compute the finite interval stuff. Fx, this formation is equals to fx e to the minus 2 pi I xc plus h, right? And well, minus fx e to the minus 2 pi I xc. This total thing divided by h dx. And subtract from minus infinity to infinity minus 2 pi I x fx e to the minus 2 pi I x c dx. Right? So this is nothing but from minus infinity to infinity, we take out all the common factors. E to the minus 2 pi I x c, this would be everything we have it, and times e to the minus 2 pi I x h minus 1 divided by h, subtract, well, or plus 2 pi I x dx. Right? That okay? I think this is just algebra, right? So I think this should be clear. So this is very good, at least good enough for us. The reason is, you can see that this part is nothing but the definition, almost the definition of the derivative of these functions evaluated at 0, right? So when h tends to 0, this should equals to 0, right? If h tends to 0. But what if h not tends to 0? Well, because you are taking this integral for x, then, well, if you want to say something about this, then at least it's not so clear whether this will tend to 0 or not. So that's again trying to use our old trick. Let's try to discuss about x. Because when x is very big, this part is very small, and this part is just something bounded. When x is not so big, then this part should be something like a derivative. At least you can take h to be something very small so that it becomes something very close to the derivative formula and it tends to 0. Okay? If x is not very small, or at least not bounded above, if x could be anything, then we cannot say that, right? Because we want to take h tends to very, 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 very small, but it has to be small comparable to 1 over x. But if x could be arbitrarily big, then this will not be very small. But if we can bound it x, then we can take h to be small enough. So we can argue it similarly as we did before. There exists some n which is bigger than 0, such that the integral of x bigger or equal than n fx dx is less than, say, half, well, 1/4 epsilon. Okay, for given epsilon, we can find some n such that this is less than 1/4 epsilon. And x is greater or equal than n, x times fx dx is still less than epsilon over 4. Because x times fx is still decaying very fast. Okay? And if we fix this n, for x is less or equal than n, you can see that we will argue when x is greater than n is very small, all this part is less or equal than x, 1 plus x. So of course, it's less than half epsilon. But if x is less than n, x now is bounded. There exists some kind of delta such that if h is less than delta, we have e to the minus 2 pi I x h minus 1 divided by h minus or plus 2 pi I x. By definition, this limit should equals to this, right? So that means when h is not so big by some fixed x or bounded x, this is less than epsilon over n, over 2n. maybe I should say 4n. Okay, is that clear? Is that clear? So this means the total integral of this kind of thing the total integral, if you want to estimate it, is less or equal than, you take x is less or equal than n, well, x is greater than n, this will take it inside, then is fx with norm, and this norm is 1, this norm is, well, is less or equal than something like 1 plus, because this part is, well, it's just something bounded above when x is very big. Well, this is 1 plus x dx, plus when x is less or equal than n, you will have fx times e to the, well, this term disappear, and e to the minus 2 pi I x h minus 1 divided by h plus 2 pi I x dx. Okay, so it's less or equal than, this part should gives you, well, some epsilon over 2. This part, maybe I should say fx is less or equal than b. And we divide b here as well. This part is less or equal than half epsilon. So eventually, everything is bounded about by epsilon, okay, for any epsilon greater than 0. So that means if we take h tends to 0, we get this Fourier transform of minus 2 pi I x f x is equals to d over dc f hat of x. Okay. Is that clear? Any question for this proof? Any question? Any question?
No, kind of looks like what we did for the
Yeah, it's
vision.
kind of the same trick we did here, right? It's just like the same trick. It's just like when x is very big, it's in some infinite domain, then your fx decay can help us. Otherwise, if x is somehow bounded, then we can use the boundedness and then we can shrink this h so that it's okay. Right? Well, the reason why we want to shrink this h corresponding to x is simply because, well, this is something that depends on x and h. So, well, if you really want to write it, you probably want to write it, if you want to write it as some derivative, you better try to write it in this way, and then you can see that, okay, this is nothing but e to the some constant, right, times, well, some kind of small number, say t minus 1 divided by t. Then you give me any t. If t is small enough, this will tend to 2 pi I t. Right? So which is why, well, we want our h, well, we want our x to be bounded about so that we can conclude, we can get hx can be arbitrarily small. It can be arbitrarily small, so these two terms can be arbitrarily close. Okay? Which is why we want that. No, I think this is 2 pi r, no t. I'm sorry. Yeah. Okay. By definition of derivative. Any question? Okay. So we have everything. We have all the properties. Now the only thing left, other than the only thing left about what I claimed before is first, we want to show that the Fourier transform of the Schwarz function is a Schwarz function. And second, we want to show that the Fourier transform has an inverse. You can take the inverse Fourier transform, and the inverse Fourier transform is somehow like the Fourier transform you take 3 times. Okay, so these two things, as long as we are able to prove that, then we are able to use the Fourier transform to solve a PDE, to try to transfer a PDE to an algebraic equation or to an ODE. Right? So let's show it. Let's first try to formally show that if f is a Schwarz function, then f hat is also a Schwarz function. Okay. So if f is smooth and decay faster than any polynomial, then so does f hat. The proof is actually pretty easy. You can see if you want to estimate the decay or whether it's bounded above or not of c to the power k d over d c to the power l of f hat of c. If you want to estimate this and check whether this is bounded or not, you just need to check whether another function is in MR or not, right? Whether another function is in this SR or not, because we know that for an MR function, if for moderate decreasing function, the Fourier transform is bounded. So if we can say that the Fourier, this kind of thing is a Fourier transform of an MR function, or even more, it's a Schwarz function, then we can see that, okay, this is bounded above. Okay, then we are done. So the Fourier transform of what function gives you this function? We already did that. Right, it's 1 over 2 pi I to the power k, and you take this multiplication on the frequency space, you take the derivative on the function space. You take the derivative on frequency space, you take the multiplication on function space. Right? So this function 1 over 2 pi I to the power k, and you take some derivative of it, and you take some multiplication of it, of fx is a Schwarz function, for sure, right? You multiply some polynomial, you take derivative, it's still a Schwarz space function. It's still a Schwarz function. So we know that this is bounded above for some v, right? So since k and l are arbitrary, f hat of c is a Schwarz function. Okay. Any question? Any question? So you can see that this kind of very good practice makes us a very, well, our Schwarz space something very useful, okay? By the way, you can check it yourself. Although this practice, we say that is true for Schwarz function, but at least some of them are also true for the moderate decreasing functions in MR. For instance, this one, and this one are both true for the moderate decreasing function. But is this one true or not, or this one true or not? You can try to check yourself, okay? For functions in MR, whether these two are true or not. Of course, if Schwarz function, then everything is true, okay? And you have a perfect duality between a function and the Fourier transform of this function, simply because you have this theorem. The functions and the Fourier transform of these functions, if you have one in Schwarz space, you have another one is also in Schwarz space. Okay. Any question? Okay. Last 7 minutes, what I'm going to do here is, since we're trying to study the Schwarz function, right? And it seems that we do not have any examples about the Schwarz function other than the Gaussian, if we want to write it down. Other than Gaussian, we cannot really know what is the Fourier transform of your functions, right? So let's try to calculate the Fourier transform of Gaussian and see, well, what do we get, okay? Because we do not have any other example.
Wait, why was Gaussian a Schwarz function? Because I think Gaussian was non-zero everywhere.
It's non-zero everywhere, so it's not a function that is smooth with compact support. Remember, we say that the smooth function with compact support is a Schwarz function, but of course, well, Schwarz function may have some other kind of function like Gaussian. Don't mix it up, okay? Don't get these two things messed up.
Okay.
Yeah, the Gaussian is the only one that is easy to write down, and it's a Schwarz function, right? It's the only one, almost the only one. So if we want to see what is the Fourier transform of Gaussian, you take the Fourier transform of it. Let's say this is FC, okay? And it's equals to integral from minus infinity to infinity e to the minus x squared times e to the minus 2 pi I x c dx. Okay, we want to find what is the Fourier transform of it. Maybe let's try to guess something before that. For instance, it might not be very easy to calculate it. What if let's try to find what is f0 at the very beginning, the easiest one, which is you kill this term and only keep this one. The total integral of Gaussian. Anybody had heard about how to find the total integral of Gaussian?
We've learned that in Math 205. And
oh, really? That's great. So then that'll be good, because then that means it's actually the square root of the square of it, right?
yeah, and do the change of variables, like
Yes, that's great.
X squared plus Y squared equals to R squared, something like that.
Exactly, yeah. E to the minus x squared dx and e to the power minus y squared dy. So it's square root of minus infinity to infinity e to the x squared plus y squared and dx dy. This is amazing. I think this is amazing stuff in math. It's very interesting. And then you can do a change of variable in R2. Then what you get is R e to the minus R squared dr d theta from minus infinity to infinity, your dr from 0 to 2 pi, which gives you, okay, finally it's 1. Okay, this is amazing thing. So we know what is f0. Now what if you could see is not equals to 0? What if you could see is not equals to 0? Fc equals to, well, from minus infinity to infinity e to the minus x squared e to the power minus 2 pi I x c dx. Okay. In order to find that, let's try to do something like this. Let's try to take derivative of it. Okay. If we take derivative of it, you know that, okay, it must equals to something, right? But if we take derivative of it, intuitively, what we should get is, okay, it must be this Fourier transform of a function by our proposition of minus 2 pi ix, right, times fx times e to the minus 2 pi ixc dx. The derivative of the Fourier transform is equals to 2 pi ix times your function's Fourier transform. Okay? But what it is? 2 pi ix. This is minus 2 pi ixc. Right? So, well, it's actually equals to, from minus infinity to infinity, if you do a change of variable, it's f prime of x e to the minus 2 pi ixc dx with the I here. Okay? Well, you can do it yourself. It's just a change of variable. It's just increase my part. And at infinity, it disappears because f is, it decay very fast. So, which means it is a derivative. You take the Fourier transform. It's nothing but I times 2 pi ixc times the Fourier transform of your function f. Now, well, this f is this function. I just don't want to write it everywhere. Okay, so it's just the Fourier transform of your fx, which is minus 2 pi c fc. Great, we got an ODE. We got an ODE for your Fourier transform of Gaussian. How to solve this ODE? How to solve this ODE? Any idea?
Well, for this one, I think just do separation of variables and integration both sides. Can we do that?
It's not really, the name is not really called the separation of variables. You just divide fc both sides and take the integral, right? And then you'll find on the right hand side is log fc, right? On the left hand side is, well, minus pi c squared. So f c must equals to some constant times e to the minus pi c squared. Right? Moreover, we know that f0 is equals to 1. So c equals to 1. So the Fourier transform of Gaussian equals to e to the minus pi c squared. It's still a Gaussian, just a dilation of Gaussian, right? Which is super nice property of Gaussian. So I will stop here, and we will see more about how we can apply those kind of Gaussian to find the Fourier inverse of a function next time, okay, next week. Okay, now that's the end of this class, today's class. If you have any question, I'll be here until 6 o'clock. If no, feel free to go, okay? See you then, see you next week.